today my talk will be about confidential provider selection in collaborative healthcare peer-to-peer networks. Patient data records in the healthcare domain are often naturally distributed over the archives of corresponding doctors and healthcare facilities. Shared access to this data would be beneficial for many scenarios, for doctors as well as for the patients. However, it is unlikely that all institutionally independent doctors and hospitals in a collaborative healthcare network can agree on a single trusted certain authority to enforce access control on the data. This setup would benefit from using sharing and search technologies available for peer-to-peer infrastructures. This setup would benefit from using sharing and search technologies available in peer-to-peer infrastructures. There is a study on computational technology for effective healthcare, where the importance of peer-to-peer networks in medical informatics is stressed. Such networks could improve data sharing between doctors and hospitals in the national as well as international context. However, if we consider the high sensibility of the personal confidential data, privacy-preserving mechanisms in this context became unavoidable. For example, in case of emergency, information about blood group, allergies, and vaccinations of a patient must be accumulated from collaborative network peers and presented to an authorized emergency physician to enable rapid and informed treatment decisions. This information is spread among physicians, internists, and hospitals that treated the patient in the past. These peers need to be identified very fast and requested to provide required information. A naive approach to locate doctors for a particular patient would be just to broadcast the query to all available peers, but the disadvantage is that broadcasting is inefficient or infeasible on larger networks. On this slide, we observe an ordinary inverted index, where for each patient in the left column, there is a list of doctors he has visited in the past. Such inverted index is very efficient. It helps to precisely locate patients' medical records, but it does not provide any required confidentiality guarantees. In our work, we enhance the index in order to ensure its confidentiality. Especially, we want to prevent adversary from answering particular questions of the index. Questions like: determine the number of peers sharing patients' data of the network. Determine whether a patient record appears at a particular inaccessible size or at any indexed size. Finally, the adversary should be not able to reconstruct the list of records shared by a particular peer on the network. In peer-to-peer, DHT is a family of distributed algorithms typically applied in the mainstream peer-to-peer systems. As the name implies, the functionality of DHTs is similar to the functionality of traditional hash tables. They enable efficient distributed storage and retrieval of key value pairs. Thereby, an ordinary inverted index can be partitioned across several peers. In our scenario, we want to use as keys the patient names. Therefore, patient names are converted to numeric representations by using a consistent hash function. On this slide, we can observe three different parts of the indexes stored on a particular peer. First of all, the DHT finger table, which helps to locate a particular peer using its ID. The next part is inverted index, where for each patient a list of the doctors is stored. Finally, in the last part, for each patient his medical record is stored directly on the doctor's peer. Retrieval occurs in two steps. The first step: find all doctors that this patient has visited. The name of the patient is transformed to a numeric representation, then the peer responsible for holding this value in the DHT is located. In the second step, the peers corresponding to these doctors are contacted directly for authorized clients, such as emergency doctors, to retrieve important information for the patient, for example, his allergies, medication, and past illnesses. Each doctor peer authorized or denies the access to its documents independently. Our system modifies index content. Each posting list in this index is a bitmap. Like in ordinary inverted index, this list corresponds to a patient. Each posting element, bit in this map, corresponds to a content provider. This bit is set to 1 if the corresponding provider shares information about the entity, and to 0 otherwise. Note that in general, a posting element may contain additional data shared by the content provider. Now to encryption. In our work, we are using Shamir's sharing scheme. The essential idea is that 2 points are sufficient to define a line, 3 points are sufficient to define a parabola, and 4 points to define a cubic curve, and so forth. That is, it takes k points to define a polynomial of degree k minus 1. Every participant in our network is given a point, an integer input to the polynomial, and the corresponding integer output. Given any subset of k of these pairs, we can find the coefficients of the polynomial by solving a system of linear equations. The secret is a constant term a0. This scheme avoids complex key management and does not require re-encryption of the data unless more than k peers in the network are compromised. This slide illustrates a part of peer-to-peer network with peers p1, p2, p3, and with n equals to 3. The posting list for the entity E1 is encoded into 3 posting lists, each presented as a random vector. Each of those vectors is stored on a separate peer. Assume k equal to 2, then in order to decrypt the elements corresponding to the entity E1, the user needs to be authorized by at least 2 peers out of P1, P2, and P3. In order to measure feasibility of our approach, we use the data from the World Health Organization. According to that data, the number of physicians in the majority of the European countries does not exceed 300,000, and 80 million is a maximal estimate for the population. The proportion of the physicians with respect to European population does not vary much, and the proportion physician persons can be estimated as 1 to 450 on average. Using these boundaries, we created a matrix index. We assumed normal distribution of the number of doctors per patient. On average, a person has her data by 20 doctors. We use this number as a mean for the distribution. Patients are uniformly distributed by the doctors, around 5,000 patients per doctor. Thus, each patient was assigned to 20 randomly chosen doctors on average, and each doctor served on average 5,000 patients. Assuming a bit of storage for patient-doctor relation, the index requires only 25 kilobytes for each patient's bitmap. The key out of n encryption additionally increased the size by n. We did several experiments to measure the network cost and storage overhead for our approach. In this figure, we vary k and n parameter along the x-axis, and the y-axis shows the number of network messages required to create an index. The parameter k determines the security level within the network. The parameter n, on its turn, determines the number of times the index storage has to grow. Parameter n determines the robustness. The greater n, the more peers can be offline without influencing the index effectiveness. The cost for creating an index occurs only once, when bootstrapping the network. In this figure, we plot the costs for querying and updating. The number of messages needed for the retrieval of a particular posting list increases by k times compared with an ordinary DHT, because of the encryption. However, even for k equals to 6, retrieving of the patient's information requires only 54 messages. This number of messages is negligible and can be easily executed in real time. Cost for the update grows linearly with n. This happens because the content provider needs to locate the peers that hold all the n bitmaps for the patient and update 1 bit at each of them. For this update, the whole list need not to be retrieved. Similar to query cost, this cost is also negligible and can be executed in real time. For the storage overhead, Schemmer's k out of n scheme does not change the size of the posting list element, although the number of posting lists in the network increases by n times. The figure shows that the storage overhead increases linearly with the growing number of n. For all the proposed setups, storage costs per peer does not exceed 60 megabytes. This storage overhead is negligible for today's off-the-shelf personal computers. In our work, we considered the challenges involved for building a confidential index over a peer-to-peer healthcare network and discuss initial solutions. For a current setup, a medical network in Europe, it is feasible to maintain a matrix-based index with confidentiality guarantees within a peer-to-peer-like network. For the future work, an interesting direction would be to reduce index matrix by keeping its confidentiality guarantees. Thank you.